So, lots of ideas here. How do you study it? You gotta work on reading the text, but also trying to remember what things mean without looking at the text. You gotta practice problems. You need to spend time thinking about concepts too, if you're really gonna get things. We're not after full rigorous proofs of things in this class. What we're after is intuitive conceptual understanding, which comes through making graphs, thinking about the graphs. It also comes through thinking about examples and how the concepts that we talk about relate to the examples. We will come to the example to illustrate this idea again here in a minute. You're not going to have to know this more general one for the test, but I wanted to get it on there for the record. Okay, if you've got n random variables and n constants, that you can do that. Okay, but for the record, that's true, but it's not something you need to know typically. And for the test, you won't. Okay, all the theoretical stuff does have practical importance. We are going to come to this example here again that we talked about last time. Before we do, let me also mention that you can calculate the variance of the random variable. And I got to get my mean over here. And the standard deviation of the variable, which again are supposed to model variances and standard deviations for data. That's the idea. These are all models. That means they're imperfect. When you try to apply this stuff to real life, it's only approximations. And you try to test and see how good the approximations are, and then refine your model if they're not real good. Okay, they're all models in real life. Anyway, formulas, I'll put the variance one up on the board. Because we'll use it here in a minute. And the standard deviation, this is also called sigma squared. The standard deviation then is the square root of the variance. Okay? So let's do that as an example. Let's go ahead and go back to that example with the product development. So once again, X is the number of weeks for the development of product specifications, and it costs $7,000 a week. Y is the number of weeks to complete the design of the manufacturing process, and it costs $25,000 a week for that. We've got these probability models for the numbers of weeks of each of these things in these two columns. Last time we calculated the mean for X as 2.1. You can expect the product specifications to take about 2.1 weeks. And the mean for the Y you can expect to be higher at 2.95 weeks. Let's calculate the variances and standard deviations for these as well. We'll do it in the spreadsheet, but you should be able to do it by hand with calculator help on the test. What else do we want to calculate? We'll look at the formula. Okay? We want to calculate the sum of these products. I need to find these differences, square them, and multiply times the corresponding probabilities. Add those up, and that's called the variance. Then take the square root of that to get the standard deviation. So I could, for example, do it in one more column, essentially. And that would be fine for the test, too. I could label it X minus mu squared times P. That's probably the best label for it. On a spreadsheet like this, what would I do? The different X values are over here, 1, 2, 3. I label them with K. K is my label for the arbitrary X value. So I'd take that arbitrary X value. I'd subtract the mean, which is down here in cell D13, and I want that to be fixed. By the way, if these are always too small for you to see way back there, you might want to consider moving up sometimes. So I typed here equals B6, that's the first value of X right there, minus $D, $13, which is the mean. That's the mu. Squaring that, I'm going to have to multiply now times the corresponding probability, which is in this column, column C. Those are the probabilities. Those are the P values. So I multiply times that. I need to do that for each. Then I need to add those up to find the variance. Equals sum. Well, I'm just going to do it for X here instead of Y. Sum of those is going to be the variance, and then the standard deviation is the square root of that, which I can do with equals SQRT. I can also raise it to the 1/2 power as an alternative way to do a square root. Same thing on your calculator. You can use the square root button, or you can raise it to the 1/2 power to do a square root. Square root of 0.49, hey, that's kind of nice. Actually, it's exactly 0.7. Here, this one turns out to be exactly 0.7 for the standard deviation. Okay? Maybe I better do it for the other one, actually. Let me quickly do it for the other one, if we're going to combine these variables. Actually, I should have labeled this y times p instead of x times p, because this variable is called y. And this y minus mu times p, y minus mu squared times p. Same kind of formula. The y values themselves are over in the k column, minus the mean, which is in this case k13, use dollar signs, times the p, the probability is in column j. I'll just make these bigger here for you. Look at the formula up there. Take a second to look it over and see that it makes sense. Y is in column I, k13, that's where the mean mu is. J, that's the probability column. Add those up, that's the variance. Oh, come on. I don't like that, put that in front of me. Sum, use numbers, that's the variance. Standard deviation is the square root of that. Okay, about 1.12. All right, what I want to illustrate now, so what we found here is the standard deviation of the x in this situation is 0.7, and the standard deviation of the y, it's approximately 1.12, let's just assume it is 1.12. I'd like to use a couple new formulas now that you should know for the test as well. Formulas that are on another slide here. This one down there. Oops, actually the previous slide. This one. Yeah. Actually, sorry. Okay, well let's go ahead and use this one. Okay? This formula down here at the bottom for the standard deviation of the sum of two variables is true when the variables are what we call independent. Okay, and if they're not independent, it's only approximately true. What does independent variables mean? Basically, it means they're unrelated. Knowledge of the value of one of them doesn't affect your knowledge of the value of the other. Basically. Okay? Don't worry about whether that really is true here. Many times it's reasonable to assume it's approximately true at least, and people use this formula anyway. X is the number of weeks for the product specification. Y is the number of weeks for the manufacturing process design. Are the values of X and Y independent in real life in this company? I don't know. If these two teams that work on product specification and manufacturing process don't talk to each other, they work in separate states maybe, it might be more reasonable to assume they're independent, that knowing how long the product specification took and knowing how long the manufacturing design takes might be unrelated, okay? I don't know. Many times we'll go ahead and assume they're unrelated, that they're independent, without that necessarily being true, so that we can use this formula. But realize in real life that that assumption might not be warranted, or it might only be approximately true, and so this formula itself only gives you an approximation. How would you use it here? And what would it represent? Well, to use it here, you would do this. Which, by the way, is not equal to 0.7 plus 1.12. Try it with your calculator. It's not equal to that. You should not assume it's equal to that. You should actually do the squaring, adding, and the square root. I'll illustrate it here. 0.7 squared plus 1.12 squared is 1.7444. Raise that to the 1/2 power. That's the same as the square root. The answer is about 1.32. That's not the same as 0.7 plus 1.12, right? 0.7 plus 1.12 is different, 1.82. Not the same. Don't expect it the same. You've got to do the squaring, adding in the square root. The square root of a squared plus b squared is not a plus b. That doesn't work for square roots. Okay, that's a common mistake. That's why I'm emphasizing it. What does it mean? Pun intended. Okay. Again, you got these means for the mean number of weeks, 2.1 for that one, 2.95 for that one. We found the standard deviations for the number of weeks, for these models, these theoretical models, that don't necessarily perfectly match reality. The idea would be, well, okay, what's the mean of the combined variable x plus y, and what's its standard deviation? Which is relevant for real life, because you want to know how long the total process put together takes, on average, and what's the standard deviation of that. On average, when you put these two processes together, it takes 2.1 plus 2.95 weeks. What would that be? That would be what, 5.05 weeks, on average, if you do this process over and over again, over many years. Okay? What's the standard deviation in the number of weeks total? It's about 1.32. This is just an approximation. That's probably too many significant digits. A little bit more than 1 week is what you would say. And that should be approximate, a model for standard deviation of actual data when you actually do these processes together. So it gives you approximations to quantities that might be of interest to you as a manager, if you're worried about costs. You can also, it turns out, write down a more general formula. In particular, this one, that would allow you to take the costs into account. The A could be the $7,000 per week, and the B could be the $25,000 per week. Plug into that formula to find the standard deviation of the total cost, not the total number of weeks. This has a more generalized form too, but you don't need to know that one for the test. You should focus on the first one. Again, for the example, A is 7,000, B is 25,000, and the combined variable AX plus BY is the combined total cost. X plus Y itself is the total number of weeks. 7,000X plus 25,000Y is the total cost. And that would be the standard deviation of that combined variable, the total cost. Okay? Again, assuming X and Y are independent. Maybe that's a reasonable assumption, maybe it's not. We will assume it's true for the test, for the sake of having simpler formulas. If they're not independent, the formulas are much nastier. Okay? So we're making this kind of simplifying assumption to make the math nicer. All right, remaining time, I'm going to talk about the law of large numbers and the central limit theorem, which you really can't talk about in full depth in 10 minutes. But I do want you to know the basic idea for the exam, so I'm going to try to focus on the basic idea. Their statements are kind of complicated, though. And, you know, math speak. Draw independent observations at random from any population with finite mean mu. As the number of observations drawn increases, the mean x bar of the observed values gets closer and closer to the mean mu of the population. Whoa. Oh. Okay, what's going on there? It's similar to the idea for p hat, approximating p, and the graphs I showed you earlier. In fact, I'm going to show you graphs for this one too. All right, as you keep taking more and more trials, making your sample size bigger and bigger effectively, making n bigger, and calculating a running average, so to speak, the value of x bar, as you keep calculating, should get closer and closer to the true mean of the population, mu. If you make a graph, you'll get some ups and downs. Those ups and downs should sort of settle down as your sample size gets larger and larger, and the graph should be approaching the true mean of the population. That's the basic idea. It gets closer and closer to the mean. There's this assumption of independence. We're assuming that it's really random sampling, essentially, that the value that I get from the next sample is independent of what came before. The technical assumption to make this true. It's also related to the sampling distribution of x bar. This says that if you're doing simple random sampling, and x bar has a sampling distribution, effectively is what we're talking about here, that is, well, it typically will be approximately normal, we will see with the central limit theorem. Let's go ahead and pretend it's normal. That will be centered on the population mean, mu, and have a certain spread, measured by that distance right there. That spread will be equal to sigma over square root of n, is what this is saying, when n is the sample size. Mu is the population mean, sigma is the population standard deviation. What this picture is supposed to be is a picture of the sampling distribution of x bar. A model for the values of x bar over many, many samples of the same size n. With the law of large numbers, you're imagining n increasing. You imagine you keep taking another value and calculating an updated mean. Here you're imagining n as being fixed. For any fixed n, you can draw a sampling distribution. Again, modeling how the values of x bar change over many, many samples of that same size n. If it's unbiased, it'll be centered on mu. That'll happen if you're doing simple random sampling. Does it look exactly like a normal curve? Well, when your sample size is small, it doesn't necessarily. Especially if you're sampling from a non-normal population. But it should be approximately normal, and the approximation gets better and better as the sample size increases. The spread, again, is given by this thing, sigma over square root of n, which is good because what that tells you, again, is that the sample size is larger. That's going to reduce that standard deviation, giving you a taller, skinny sampling distribution, which means, as long as you're doing simple random sampling, that your values are not going to vary very much around the true mean, which is what you're after. The mu is the population random. Lots of words here. Listen, you might want to listen to them again if you're feeling like you're falling asleep, okay? Because pretty much every word I say is important if you really want to understand stuff. If the population happened to be exactly normal, the next slide says, the first box says that the sampling distribution is exactly normal. That's not typically the case, okay? Rarely is the population exactly normal. This is more of a theoretical thing. More importantly, it applies to all populations. There's the central limit theorem. Okay, use your imagination. You can write these things down now or after class, but somehow use your imagination as we go. Okay, because I might ask you true-false questions about this. I might ask you conceptual questions about this related to what I'm saying right now. Again, we're assuming simple random sampling because it makes the math simpler. It makes this stuff true when you're doing simple random sampling. When you're not doing simple random sampling, even if it's a probability sample like stratified random sampling, this stuff is not true as stated. The simple random sampling assumption makes the math simpler, even though this is complicated looking. Okay? It makes the math doable. You got a fixed sample size n, okay? If n is fairly large, how large is fairly large? That's not real precise. For our purposes, typically 30 or 40 or larger is typically good enough to make this approximation pretty good. This is called a theorem, but as it's stated, it's really not a theorem because it's too vague. Okay? This word approximately is too vague. It's good enough for us, though. Okay, we're not after proofs. We're after intuitive ideas. When n is large, the sampling distribution, keyword there, sampling distribution, of x bar, the sample mean, is approximately normal. Using this symbolism. Normal with the mean mu, which is the population mean, and standard deviation, sigma over square root of n, the population standard deviation divided by the square root of the sample size. Exactly this picture again. Which is what I keep drawing. I keep saying the word sampling distribution. You got to understand the idea of that. What is it? Say it again. I can never say this enough. Sampling distribution. It's a model. What is it a model for? It's an approximation for histograms that you would get if you did many, many values of x bar with many, many simple random samples of the same size n from the population, over and over and over and over again. You could literally do it. Hardly anybody ever does, though. Too much time and money. Too boring. You could simulate it. That's a bit more fun. Simulation's kind of fun. You can simulate it over and over and over again. Get a bunch of different values for x bar. Hopefully they're not too far from you. Hopefully they're all close to each other. That models the histogram you get if you make it. Or a stem plot you get if you made a stem plot. It's centered on the true mean because of the simple random sampling. It's got a certain spread there. And it is approximately normal. That's the extra thing here. Even when the population data is not normal. Okay? That's still a pretty good approximation to the sampling distribution. Here's an illustration of it with an example that I don't have time to go through the actual spreadsheet stuff. But I want you to understand the concept of what I did here. Okay, I did on a spreadsheet, and maybe I'll share this with you after class, and you should look over it if you want to try to understand it better. I used random between to get random numbers. I actually went from 0 to 10 instead of 1 to 10. The reason I included 0 is so that the mean, the true mean of the population is 5 exactly. Halfway between 0 and 10. If you use 1 to 10, it's 5.5. I wanted a true mean of 5. So it's a uniform distribution essentially for the population from 0 to 10, whole numbers, 0 through 10, 11 whole numbers. The mean of those is 5. I wanted to take samples of size 100 and first make a trial series for the running average as I kept making the sample bigger and bigger. Is this a graph of? This is a graph of the x bars, the means of these numbers that I get from random between. The first number evidently was a 7, because the first x bar is a 7. The second number evidently was what? Well, maybe, might have been a 10. 7, the average of 7 and 10 is 8.5. Okay, I guess that does go up to 8.5. Looks like it. Okay, the third number was lower. This graph goes down. In the long run, look at this. It's approaching 5, which is the mean of the population that ran between is modeling when I sample it. So I make this trial series. This is illustrating the law of large numbers. X bar keeps getting closer and closer in general to 5. The mu is 5. This is an approximation to the shape of the sampling distribution. I did samples of size 100 over and over and over again. I think I did it 45 times this time. Again, I'll share the spreadsheet with you. In each case, I calculated x bar. The sample mean with ran between with samples of size 100. I got columns of 100 numbers in them. Calculate the mean. They're all fairly close to 5. And that's what this graph is showing. They're all between 4.4 and 5.5, in fact. It looks fairly normal, fairly symmetric, close to being centered on 5 like it should be. 5 is right there. What's the spread? Approximately that distance, which is approximately 0.2. Oh, I should have done this beforehand. I forgot the standard deviation of population here. I think, if I remember correctly, the standard deviation of a population generated with that might be, oh boy, I might get into trouble. Might be around 1 over square root of 12 or something. Is that right? Okay, I'm gonna have to figure that out after class. That's probably wrong. This should be sigma over square root of n, where n is 100. Square root of 100 is 10. Where sigma is the standard deviation of the population. I don't remember what it is. I better calculate it after class and send it to you. Okay? So you can compare that. It's approximately 0.2. I hope. Okay? But that's the idea of the central limit theorem. The original population is definitely not normal. It's a uniform distribution. Equal probability for each of the numbers between 0 and 10. Each of the 11 numbers, whole numbers. But the mean follows a distribution that is approximately normal. Centered at the true population mean of 5 and with a certain spread. That's illustrating the idea of the central limit theorem. Getting close to being out of time. Where'd my clock go?
It's over here next to 12:20.
12:20? Okay, over there. That is. Okay, I've got in this PowerPoint a summary of things to know from chapters 1 through 4 that's not necessarily comprehensive. Here's what I got for chapter 1. We don't have time for you to write this down, but you probably will want to look at it after class. I summarized chapter 1 in this way. You got to be able to make lots of different kinds of graphs, especially stem plots, histograms, box plots, and time series are the most common ones that I test people about. But you should be able to make pie charts and bar charts, Pareto charts, order the bars from highest to lowest. Bar charts are easier to make. Pie charts are tricky because it's hard to get the angle right. If I had you make a pie chart, I'd probably help you. I'd maybe give you a circle, and maybe I'd even give you the angles, and you just got to fill in the labels. Maybe I'd have you read a pie chart. You should be able to read pie charts. The most important are stem plots, histograms, box plots, and time series. Calculate numerical summaries, mean, standard deviation, 5-number summaries. Know the formulas, possibly make a table is what I meant to say there to do the calculation, but also be able to find them on the calculator. Have the knowledge about what's sensitive to outliers. The mean and standard deviation are certainly sensitive, although the range is more sensitive. The max and min are more sensitive. The median and quartiles are less sensitive. They're not as affected by outliers. Have that basic knowledge, what I just said. Making use of normal curves in 2 ways. Percentage calculations, calculate the z-score and use the table to find an area, which will correspond to a percentage, and in chapter 4 corresponds to a probability. X-value calculations given a percentile. In other words, use the table first, backwards, to find the z-score, and then sort of undo the equation for the z-score to find x. We've done that. We have done that before. Okay? And there's the 68, 95, 90, 90.7 rule as well. Chapter 2, we can also summarize with plots. Oh, I forgot to say, be able to describe plots. Be able to describe distributions, shapes, center, spread, those kinds of words. Be able to describe scattered plots. Is it an upward trend or a downward trend? Is it a strong trend, moderately strong trend, weak trend? Is it a linear trend or a nonlinear trend? Those are the kinds of words that you want to talk about. The correlation measures the strength of a linear trend. Better R squared does, although the correlation tells you the direction, positive slope or negative slope. Identifying outliers and influential observations. Actually, the influential observations I was going to talk about briefly today, but my Mathematica wasn't working, so you don't need to know about influential observations. Mathematica is back to not working again on this computer. Do calculations, know the formulas, be able to use them, including the SS formulas, and if you look at old tests and practice problems, you will see SS formulas come up. Be able to also calculate predicted values, residuals, and SSEs, sum of the squares of the errors, again the word error being synonymous with the residual. Know properties of correlation and regression as well. We talked about those plenty, right? We talked about those plenty, those properties. Plenty of PowerPoints in the book. And know pitfalls, maybe an essay question related to pitfalls. Chapter 3, understand some terminology, difference between observational studies and experiments, be able to identify them. Related terminology, for experiments, there's the factors and the levels and that kind of stuff. Know what makes a good experimental design, maybe true, false, multiple choice questions, maybe a short essay question related to those ideas. Simple random samples, be able to use the table of random digits even if you've got 2 digits at a time. Understand the more terminology, populations, parameters, sample statistics, sampling distributions, which we've focused on today. Center, is it biased or unbiased? That's related to the sampling design. Spread, the variability, that's related to the sample size. The bigger the sample size is, the less spread. And chapter 4, which we really focused on a lot today. Okay? So, lots of things, okay? It takes time. You've got to make sure you have that time, put that time in, and don't cram at the last minute. It doesn't work. Okay? Wish you well. Pray for you this weekend.